This video is going to cover intermolecular forces. Intermolecular forces are the sometimes repulsive but mostly attractive forces between compounds, individual units of compounds. We tend to only think of intermolecular forces in terms of covalent compounds because ionic compounds, we have a complete positive and a complete negative charge that comes together for each formula unit. Whereas for covalent compounds, depending on whether they're polar or non-polar, they will have different interactions. So intermolecular forces are what keeps things as solids or liquids at room temperature. And there are three major types of intermolecular forces. So let's say these intermolecular forces are mainly for covalent compounds or molecules. All right, so there are three major forces. And van der Waals forces or dispersion forces are found between all atoms in these compounds and all molecules. So all molecules can have intermolecular forces, and these are mainly for non-polar compounds. Whereas dipole-dipole forces are found where we have dipoles. Well, remember, dipoles are slightly positive and slightly negative ends for a polar covalent compound. If we take a look over here on the side, notice that we've got these polar compounds, water and chloromethane, where we have a dipole here going towards the oxygen, and we have a polar molecule. This red heat map shows that most of the electrons are found in that area. Chloromethane, notice we have one chlorine and three hydrogens, and we have a dipole going up towards the chlorine atom. So polar molecules can undergo dipole-dipole forces. Whereas, notice these molecules down here, they have no net polarity, so they will interact with each other via van der Waals forces. Hydrogen bonding is a special type of dipole-dipole interaction, and it is a strong dipole-dipole interaction. And we'll take a look on the next slide as to when this type of interaction occurs. And it only occurs between certain types of molecules. So if we're looking at the weakest to the strongest, dispersion forces are the weakest and hydrogen bonds are the strongest. Note that the strongest type of interactions between atoms are going to be ionic interactions between ions, right? But that's not what we're talking about here. So, dispersion forces or London forces occur between nonpolar molecules. Notice that these molecules here on the top, they have an equal sharing of electrons, right? And they don't tend to have any charges between them. So what happens is sometimes one molecule, all the electrons will arrange themselves on one side of the molecule. And once that first molecule arranges itself, the one that's right next to it will arrange itself so that its negative end will be close to the positive end of the molecule next to it. It's kind of like, you ever notice when one person yawns? If you're watching that person yawn, you yawn too. So this is called an induced dipole. So a dipole is induced instantaneously. And the larger the molecule, the more of these forces. So the bigger this molecule gets, the bigger these molecules get, the more and more forces they have between them. And the way that we can determine the strength of the intermolecular forces is by looking at the boiling point. So 2-dimethylpropane has a boiling point of 9.5 degrees Celsius, whereas pentane has a boiling point of 36 degrees Celsius. Well, if you notice, this molecule is like a ball, and it's really hard for it to get close to another molecule just like it. They'll bounce away from each other. But if you notice that pentane is flat and long, it can stack on top of each other like lasagnas all around, and they can get really, really close to each other. So molecules that have high surface area, like pentane, will have more dispersion forces than something that has low surface area, like this 2,2-dimethylpropane. All right? So which one of these would have the stronger dispersion forces? The pentane, because it has larger surface area. So dipole-dipole interactions, we have, if these are representing 4 different molecules in a soup of a polar, some polar pure substance, all of the molecules already have dipoles present in them. Notice I've got a slightly negative and a slightly positive end to these molecules. An example of that is acetone, where I've got this oxygen up here, and it's giving me this polarity in this direction. So that molecule always has a slight positive and a slight negative end. So these molecules will line up slight positive to slight negative. And those are dipole-dipole interactions. Notice that London dispersion forces are just, instantaneous dipoles. They don't have a permanent dipole, but every so often a dipole will form, right? So these things would be something like wax, Vaseline, or let's say oils would have these type of London dispersion forces. Whereas polar molecules, water is a liquid at room temperature, but let's see, what's another polar molecule? Depending on the, polar molecules tend to be liquids at room temperature. Some of them can be solids at room temperature. So some other ones are alcohols, methanol, propanol, ethanol, some of the acetone, some of those things are going to be polar, but they tend to be liquids to solids. A lot of them are liquids. Now, hydrogen bonds only form between certain compounds. These compounds have to contain hydrogen oxygen, hydrogen fluorine, or hydrogen nitrogen bonds. If there is not a hydrogen nitrogen, hydrogen fluorine, and hydrogen oxygen bond, there is no way that hydrogen bonds can form. Notice that we've got ammonia here, NH3. Notice I've got a nitrogen bonded to a hydrogen. So the hydrogen of one molecule will be attracted to the nitrogen of the next molecule. And because this interaction is so strong, we call it a bond, right? So hydrogen bonds can only form between polar molecules that contain these hydrogen-nitrogen, hydrogen-fluorine, or hydrogen-oxygen bonds. Now we're going to take a look and do some practice in determining what the intermolecular forces are between these compounds. Now, notice we were looking at the actual structure of these compounds. So how can you figure out what the intermolecular forces are? First, you have to determine if the compound is polar or nonpolar. Well, how do we do that? Well, if it's just 2 atoms, then we can look at the bond between those 2 atoms. And we know that it's polar or nonpolar. If it's a whole entire compound, what do we have to do? You have to draw the Lewis structure to see if it's polar or nonpolar. So nitrogen gas is essentially nitrogen that's triple bonded to itself. And because it's two of the exact same atoms, it's going to be covalent. It's going to be nonpolar covalent. So all nonpolar compounds are going to have only dispersion or van der Waals forces. Van der Waals. Right? All right. Carbon tetrachloride. We saw this a little while ago. It was one of the structures that we drew. Notice that, let me draw it over here. Notice that it is, even though each one of those carbon-chlorine bonds are, I'm not drawing the outside electrons because you know that we have these 6 electrons on the outside. I will draw them. Although we have these large electron clouds around these chlorines, this whole compound is nonpolar because it's symmetrical. So if it's nonpolar, then that means it must also have dispersion and van der Waals. Now notice that the question says to determine the main intermolecular force. So remember, all compounds or all molecules are going to have dispersion forces, but there are some forces that are stronger than others. Remember this H2S, we drew it already. And we already know that this is polar, right? So if it's polar, then that means we can have dipole-dipole interactions. Hey, wait, I see hydrogen. Can it have hydrogen bonds? No, because this is sulfur. And sulfur cannot undergo hydrogen bonding. All right, what about sulfur monoxide? We haven't drawn this guy, but sulfur monoxide is drawn this way. You can take the time to count the electrons and draw the Lewis structure yourself to determine. And if we look at the polarity or the electronegativity difference between the sulfur and the oxygen, it is polar. So we have, since it's polar, we also have dispersion forces. Oh, sorry, not dispersion forces, people. Dipole-dipole interactions. So forces, interactions, these words are used interchangeably. Dipole-dipole interactions. All right, the last guy, N2H2. As I said before, you can take the time to draw the structure, but actually, if you draw the Lewis structure, you'll notice that both of these nitrogens have, it's a double bond nitrogen, and both of the nitrogens have those lone pairs. So remember we said before that if it's got those lone pairs, and notice that the nitrogens are in the center and not on the outside. So the polarity is going towards the nitrogens. Let's say it's going towards the nitrogens. Right? So the molecule is polar. Back to my red ink. And so because this is polar, we would say that we have dipole-dipole interactions, which we do. But the question is asking for the strongest type of forces. Notice that we have a nitrogen and hydrogen. So if it's nitrogen and hydrogen, these can also undergo H bonds or hydrogen bonds, and the hydrogen bonds are the strongest. And even though these three polar molecules have dipole-dipole interactions, they also all have van der Waals or dispersion forces. But we just want to know what is the main intermolecular force. So hydrogen bonds are the main intermolecular force for N2H2, dinitrogen dihydride.